Which brings us to our set of notes for today, which is types of bonds. Again, you will find a set of notes in Schoology for you to use, or you can take your own notes as always. Summary and questions at the end of this set of notes, please. All right, so when we talk about types of bonds, what we need to understand is we need to understand polarity and electronegativity. Now, electronegativity we have talked about a little bit before. It is the ability of atoms in a molecule to attract electrons to themselves. So again, being part of a molecule is required. They have to already be in a bond. Okay, and our trends on the periodic table is that the electronegativity increases as we go from left to right, and it increases as we go from bottom to top. And so on our periodic table, the trend is that we get larger and larger as we go from bottom left to upper right. All right. Electronegativity is a function of both ionization and electron affinity. Okay, so if you have a high electronegativity, you have a very negative electron affinity. That is, you gain a lot of energy by bringing in electrons. You also have a very high ionization energy. It's very, very difficult to remove electrons from you. And so you put those two things together and you end up with a high electronegativity, a very electron-loving element. All right, so what do we use electronegativity for? Well, different elements have different electronegativities. And because of that, you get polarity. Polarity tells us how equally two atoms are sharing electrons. Okay? Though atoms often form electron compounds by sharing electrons, the electrons are not always shared equally. So imagine that I have a fluorine bonded to another fluorine. Well, those two atoms have the same electronegativity. They have the same attraction for atoms, and so they're going to share the electrons between them equally. However, if I have something like hydrogen fluoride, okay, fluorine attracts electrons much better than hydrogen attracts electrons. Okay, so the fluorine pulls harder on the electrons it shares than hydrogen does. Therefore, the fluorine end has more electron density. Eventually, we start calling that the partially negative end. And because the hydrogen has a little bit less electron density, we call that a partially positive end. This is a polar bond. The greater the difference in electronegativity, the more polar the bond is. Okay, so we move from covalent all the way toward ionic. Ionic bonds have the greatest difference in electronegativity. Their difference is so large that one atom actually rips electrons away from the other. All right, so if I look at a series of compounds, hydrogen down the combining with halogens as we move down, hydrogen fluoride fluorine has the greatest electronegativity, so it is the most polar. Chlorine, a little bit less polar. Bromine, a little bit less polar still. And hydrogen iodide, less polar still. Why? Because, again, lower electronegativity on iodine, high electronegativity on fluorine. All right, so we can think of the electronegativity difference as a major determinant of what kind of bond we have. Now, oftentimes we'll see a scale set up like this, which basically says, oh, you got a low difference of electronegativity, you're nonpolar. You have a high, you're ionic. You're in the middle, you're polar. Okay, so this is a very fluid continuum. However, so you should not use these numbers as exact measurements. You should just understand the greater the difference in electronegativity, the more ionic something is. The less the difference in electronegativity, the more purely covalent or purely sharing electrons a bond is. Okay, there are exceptions. For example, that come about. We know that metals and nonmetals typically form ionic compounds, but in the case of tin chloride, it has a covalent bond because the electrons are not being pulled away enough by chlorine to get them away from tin. And so as a result, there is sharing that happens in this particular bond, and you end up with a covalent bond instead of the expected ionic bond. The other thing that happens when you have bond polarity are dipoles. When two atoms share electrons unequally, a bond dipole results. And what we end up is something is called the dipole moment, which we usually think of as going from the positive and toward the negative. Okay, you can measure it as they're separated by a distance and understanding the opposite charge of those, and you measure it in a unit called debye. None of this is super important. What is important, though, is that there is a relationship between bond length and the strength of the dipole moment, because we know that dipole moment is governed by radius. So the bigger the radius, the bigger the dipole moment. So to close out our discussion, how do I know then if a bond is ionic, covalent, or metallic? Okay, the most important thing whenever we are classifying a bond type is always going to be the properties. As we'll learn soon, particular types of bonds and particular types of compounds have specific properties. We match those properties with ionic, covalent, or metallic. The more closely they match, the more likely it is that it's one of those. Okay, so that's where we go first. Second thing we're going to look at is metal and nonmetal versus nonmetal, nonmetal. Again, nonmetal, nonmetal tends to be covalent. Metal, nonmetal tends to be ionic. And metal, metal tends to be metallic. Okay. We might also use electronegativity differences. Okay, the electronegativity differences. High difference is ionic. Low difference is covalent. The greater the difference, the more polar we get. Okay. One last thing here, metals with high oxidation states or high charges. For example, manganese can form a +7 ion. When it does that, there's our high oxidation state, and the types of bonds that manganese will oftentimes form are molecular or covalent in nature. Okay. Biggest thing to remember is all bond typing is a continuum. There's no way to definitively say this is an ionic, this is going to be a covalent, this is a metallic. We need to look at properties, we need to look at the kinds of elements making it up, and we need to look at the electronegativity differences and figure out what is the story with this particular element or compound.